Good morning, 8th grade. We're going to take some notes today about the real number system and what makes a number rational versus irrational. So I'm starting a new notebook, and this is kind of a fancy notebook. You don't need a notebook this fancy. But I do want you, mine is already set up for a table of contents. If you just have a plain notebook, that's fine, but set aside about 2 pages for your table of contents. And then, like I said, mine already has a place for a page number, but if yours does not, that's fine. Just go ahead and put page 1 somewhere at the bottom of the page. I already have a box here, but if you want to circle it so that it sticks out and doesn't blend in with the other things, that might be a good idea. All right, and then I'm going to write the topic here at the top. So let's call it the real number system. I'm going to put a box around it so it's easy for me to spot and I know exactly what we're talking about when I go back and study. All right, so let's pose a question. What is the real number system? Underline it. All right. So the real number system is all of the numbers that have a tangible value. And tangible, when you say something's tangible, it means something you can touch. And so here, in terms of real numbers, what they mean when they say tangible value is that it has, it's located on the number line. It exists on the number line. Okay? So let's talk about the different numbers within the real number system. So I'm going to make a little graph here. If you were with me in class, we did this. Actually, I think we did this in 7th grade right before we had to get shut down. All right, and I'm going to split it in half because we've really, up until the start of 8th grade, we've only talked about part of the real number system. All right, so the very first numbers, actually let me make a number line down here too, and that way we can kind of place them on the number line as we do this. Make some tick marks. Try to keep them pretty evenly spaced. All right, so the first numbers that you learn when you're first learning how to count when you're a baby or a toddler, we first learn about the natural numbers. And those are the counting numbers. So when you have like a little brother or sister or cousin and they're like 1, 2, 3, 4, those are the natural numbers. So those are the first ones that we learn. Then once we get a little bit older, we learn about the concept of 0. We add that to our number line, and those are called whole numbers. Okay? And then in 6th grade, we started learning about how there's numbers on the other side of 0 too. Negative numbers. -1, -2, -3, -4, and so forth. And all of the whole numbers and their opposites are called integers. Okay? All of these are rational numbers. So rational numbers, everything on this side of our number system, it can be a natural number, a whole number, an integer, or what we just call like a generic rational number. And the generic term for rational numbers means that it includes all these things, all these points in between the number line, right? So last year we did a lot in 7th grade with rational numbers because we had to do a lot with fractions. So in between 0 and 1 is 1/2. in between 0 and -1, I could also write it as a decimal, -0.5. And I can keep slicing them in half. So in between 0 and -0.5 would be -0.25. And I could slice that in half and I would get -1.25. And I could slice that in half and I would get -0.0625. And I could keep slicing it in half and slicing it in half and slicing it in half because there is an infinite number of rational numbers. Let's put that up here. The real number system is infinite. I'm going to put a box around that one because that's an important word. So just like, you know, Buzz Lightyear on Toy Story, to infinity and beyond, it's infinite means something that just keeps going on forever. There is no end to how many numbers there are. I could keep going forever this way on the number line. I could keep going forever this way on the number line. And I could keep going forever in between numbers on the number line, okay? Now there's some numbers that are so infinitesimally exact that we could never actually put a point for them on the number line because we just can't get that exact. So we call those irrational numbers. And those are numbers that they exist somewhere on the number line, but they're so infinitesimally exact that we can only have an approximate location. Okay? So let's write down some definitions for that. So a rational number underline that. Let me give you an example of an irrational number first. So we said that the first one that we learned about was pi. And then we talked about how a lot of times things with radical signs, not always, it has to be something under the radical that's not a perfect square. So radical 2, or the square root of 2, that's an irrational number. If you put that symbol with a 2 underneath it in your calculator, you'll get a huge number that just keeps going and going. And then, let's see, also in a few weeks we're going to talk about cubed roots. So the idea of a cubed root is something that most of them are also irrational numbers unless it's a perfect cube. So perfect cubes means you multiply something by itself 3 times and that's the number you get. So for example, 3 times 3 times 3 is 27. 27 would be a perfect cube root. That doesn't go here. But 26 is not a perfect cube root, so that could go there. So let's try to estimate. We said that pi is approximately equal to 3.14. So it would go approximately right there. That's approximately pi. But we know because that decimal keeps going and going and going forever and never repeats and never ends, we really can't find one specific spot on the number line where it belongs. We can only estimate. So a rational number can be written as a fraction. That's a big one. If you can't write it as a fraction, it can't be a rational number. Okay? So for example, 1/2, rational number. 37, oh, it doesn't look like it's a fraction, but I could just do that. Now it's a fraction. I put it over 1. 0.25, if I can convert that into a fraction, it would become 1/4. Okay? So all rational numbers can be written as a fraction. They have to have a decimal that either terminates or has a repeating pattern. So an example of those, P-A-T-T-E-R-N, forgot the N. So for example, 1/8 we said was equal to 0.125. Okay, but 1/9 is going to give me a repeating fraction. So if I have, and I don't ever remember what the repeating fraction is for that, so I apologize. I should know that. 1 divided by 9. And I get, oh, that's easy to remember, 0.11111111111 on and on and on forever. So I would also write that as 0.1 with the repeat bar. That is a number that has a repeating pattern. And this is a number that has a terminating decimal. When I do the division, 8 divided by 1, eventually I get to a stopping point and I get 0.25. The opposite of a rational number, well, I'm sorry, my brain's not working today. The irrational numbers are things that cannot be written as a fraction, and it has a decimal that doesn't end, it's not terminating, and it doesn't repeat. So everything here, it's the opposite for an irrational number. Cannot be written as a fraction. And it has a decimal that is non-terminating, meaning it never ends, and non-repeating. So it's all the things here that we said for the rational number, the opposites are true for the irrational number. So we said it can be written as a fraction for a rational number. An irrational number cannot be written as a fraction. For a rational number, it has a decimal that either terminates or repeats. And here we say it has a decimal that is non-terminating and non-repeating. So it has to both never end and never repeat. And we'll give some examples. So we said that pi is equal to 3.14, but we know that the real number for pi goes on and on and on and on and on and never ends. So we could start with 3.14, but really we want to use these squiggle lines that say approximate. And let's see, sorry. The approximate value of pi would be 3.141592655359, blah, blah, blah. I'm running out of space. It goes on and on and on forever. We don't use a repeat bar here. We just use the 3 dots to show that it goes on and on forever.